So the largest set of independent edges in the Peterson graph? Come on, come on. Okay, the largest set of independent edges in the Peterson graph? How many? Five? Where are the 5 edges?
So I did the thing with the 2K 5s, you can choose 2 from each of those.
C5s.
C5s.
Okay, so I can choose 2 edges, let's see, so which 2 edges? This one and these? Is that?
Sure.
Okay.
And then I chose 2 from the inner one, such that I guess okay. So the next I chose one that connects the 2, because there is those edges that connect the 2.
Oh, wait. So you want edges that connect?
Like 2B in your case.
In this case, 2B. Oh, okay.
Yeah, and I chose 2 from that star that don't touch B.
I should have a blue marker, but I don't. So, and then you want to choose which ones?
D, A, and E, C.
D, A, and E, C. So like this.
Yeah.
Very good. Okay, so now we have a different sort of parameter. So I'm looking for large sets of independent edges, and now we're going to look for a relationship between these two concepts. Okay, so let's see. In terms of vertices, we call the largest set of independent vertices independence number. We don't use at some books, some point we might talk about the edge independence number. The edge independence number, but for our purposes, we're going to call this a set of independent edges. We're going to call that a matching. And then we'll come up with a name for the largest matching.
So matching is a set of independent edges?
A set of independent edges, yes.
Thanks.
Okay, so if I I'm going to introduce a few new concepts that will help us determine these parameters for. Yeah, it's run out of battery, I bet. Okay, so I want to talk about a vertex cover. So a vertex, one of the things about graph theory is that a vertex cover, that names of things in graph theory hopefully make sense. They don't always make sense, but hopefully they make sense. And I'm looking at independent edges versus independent vertices. If I look for a vertex cover, what would you guess that would be? Got a guess? Do what?
Like an overlap?
So is it a collection of vertices or edges?
Vertices.
Okay, so it's a set of vertices that cover. What would we mean by that? Got a guess?
Maybe if you have so maybe you're covering matching.
More.
And so it's
More than just a matching.
an entire graph.
I want vertices to cover
The graph.
what's left in the, I want vertices to cover edges. Okay, so a vertex cover is a set of vertices so that every edge, and does he give a cover a name? He calls it Q. A vertex cover Q is a set of vertices so that every edge is incident, by the way, vertex cover. So Q is a set of vertices so that every edge is incident with at least one element of Q. Okay, that's a vertex cover. So in this case, can you give me a vertex cover of the Peterson graph? Let me make it real easy. It doesn't have to be a good one.
Every single vertex.
Every single vertex is a vertex cover, right? If I take this collection of all 10 vertices, then every edge is incident with at least one vertex in the graph. Every edge is incident with one vertex in my cover. In fact, it's adjacent. It's incident with two, but one is certainly less than or equal to 2. I want the smallest. So I want the smallest vertex cover. Can you find a smaller vertex cover? So every edge, one more time, every edge is incident with one of the vertices in this cover, let's say smallest vertex cover, C. 5? Okay, so what 5? What 5 vertices?
So the 5 vertices for the corresponding 5 independent edges.
Okay, so I have so what are the 5 independent edges? Where did we put those? Did I erase them already?
Yeah, the green and line.
Okay, so give me those 5 independent edges again.
1, 5.
1, 5.
3, 4.
3, 4.
2B.
2B.
DA.
DA.
EC.
EC. So wait a second. That would be those are a set of edges that cover all the vertices. I need a set of vertices that cover all the edges. A set of vertices that cover all the edges.
So 1, 3, 2, B, E.
1, 3. Oh, I see. 1, 3, 2, B, E. Like that?
Yeah.
Okay. Does that cover all the edges?
No.
I got a yes and a no.
And D.
I think those are our only choices. Wait a second. What about the edge 4, 5? So the edge, so this is not this is not a cover. The edge 4, 5 doesn't seem to be covered by this set of vertices. And in fact, notice 1, 2, the edge 1, 2 is covered twice. Maybe that's not the most efficient way. Take a minute at your table. Can you find a small set of vertices that cover all the edges? It'd be nice if I had 5 vertices. Stop, wait a second. What's the smallest possible it could be? How many edges are there in the Peterson graph? How many edges are there in the Peterson graph? 15. Every vertex covers how many edges? 3. Okay, so if I was lucky, I'll use the word lucky, then in fact, if I was lucky, I could find 5 vertices, each covering 3 edges, and then I would be able to cover all 15 of the edges of the Peterson graph. That would mean no 2 vertices would cover the same edge. Can you do that? You don't have to whisper.
Would 1, 3 be ED work?
You
1,
said
3 be ED.
D. Shall we test it?
I guess we don't like 4, 5. I find something else. What if we do?
We have some edges.
Say that again.
So we need 2 edges and a successful cut.
This would be time consuming. What if you just listed all 15 edges and for each vertex you also just did the check marks?
For all the edges.
Yeah. Well, time consuming.
So for the outer C5, you have to choose 3. So that means for the inner one, you have to choose 3. So I have a feeling it's going to be 6.
So what if we do BED 1, 3, 4?
We've got all the outer edges.
Can we get 1A?
BED.
You said 1, 3, 4, so yeah.
Yeah.
Because
Oh,
1A.
yeah, yeah.
Anybody?
We have 6.
6. Okay, so can anybody beat 6?
Yes.
This is not how you do it. But, okay, so you think you can come up with 5 vertices that cover all the edges?
No,
6.
6.
Okay, so you can tie 6.
Yeah.
Okay. Okay, I've now erased, and I'm still recording somewhere, I don't know where. Okay, so the Peterson graph one more time, I probably should have made it bigger. So I'm gonna choose 3 vertices, let me guess, 3 vertices on the inside, 3 vertices on the outside?
True.
Okay.
Oh. So we can choose the.
They're all kind of the same until I pick one. 1, 2, 4. C. Let's see. A, B, C. This one?
Yes, maybe north corner.
let's, at this point, let's see what edges are covered. What edges are covered at this point? What edges? Let's just imagine I'm covering all of these edges. Okay, so all those edges are covered. This edge is covered, this edge is covered, this edge. Okay. And this edge, and this edge. So far I have 4, and I need to cover, gee, it looks like I have to cover 4 more edges. But I have 2 more points,
Yes.
okay?
The lower two,
The lower 2?
yeah.
Okay. Okay, so those six vertices cover all the edges. So this is called the vertex cover number, the vertex cover number, and we'll get to how this is going to apply. Okay, so I have vertex independence number, edge independence number, vertex cover number. You're making this up. You're back in the 1930s. You're making this up. What should I define next? Edge cover. Okay, so an edge cover F is a set of edges so that every vertex is incident. What does incident mean? What does it mean for an edge? What is an incident? So vertex, an edge.
One of the endpoints is that vertex.
One of the endpoints is incident. So every vertex is incident with at least one edge, an edge in F. Okay,
Page 1.
Peterson graph.
Page 259.
I'm going to draw another Peterson graph. Okay. So how many vertices do I need so that every edge is incident with one of those vertices? Yes?
6.
6. Okay, can you give me a sec?
Well, the one that she just did, is that what you're asking for?
Oh, did she, Ying, did you give me, I'm looking for, sorry, a set of edges so that every vertex is incident, sorry. Set of edges so that every vertex is incident with one of those edges. So how many vertices are incident with a given edge? 2. So I have an edge, so there are only 2 vertices that get knocked out. So can I find a set of edges that's incident with all the vertices? Set of edges that's incident with all the edges. There are 5 edges, real quickly, that you should be able to find that are incident with all the vertices. Which 5 edges?
The ones in the independent set up there. To the right of the graph that you drawn.
Oh, these
Yeah.
5? Okay, or maybe better yet, those 5. Okay, so what I want to do is we want to develop a connection between the independence number and the edge independence number. So he talks, the book talks a lot about matchings and applications, and if you turn to page 260, does everybody have a book they can look at? Okay, so if we look at 260, so I'm just going to look at 7.2.1. So here's a bipartite graph, and we've got job applicants, A, B, C, and D. Those are my applicants, and I only have, I just gave it away, I have 3 jobs. So what I want to do is I want to match all the applicants to a job. So I'll ask it that way, can you match all the applicants to a job? Because, yeah, well, we have too many jobs. We have too many jobs to do.
Too many.
Too many applicants. Okay, so and I don't want 2 applicants working on 1 job. Okay, so there's, first of all, this relationship between the number of applicants and the number of jobs. Okay, and so I can't assign each applicant a job, an individual job. But I can assign 3 of the applicants to 3 of the jobs. Okay, so when the number of jobs is greater than the number of applicants, then we're restricted by the number of, in this case, the number of jobs. Okay? Is that clear? Because now we're going to have, that's not just the only criteria. So now let's look at 7.2.3. So just to give you an idea, this is M's. The M's are men, and the W's are women. And let's just imagine by whatever algorithm, the men pick out some women, or the women pick out some men, and the edges correspond to who they're willing to be paired off with. Notice I have fewer men than there are women. It's good for the men. The question is, can I pair all the men off with a woman that they're willing to be paired off with?
No. Kind of a dated example, isn't it?
Yeah. There's not much I can, you can change it. But, what? What's the answer?
I said no, but I think it's yes.
Because all 3 of these guys are only willing to pay these 2.
No. No, why not?
Because the women want very full, they choose the same 2.
Oh, woman 1, 3, and
Man 1.
what's that? Woman 1, 3, and 5. Sorry. What you can say?
The men 1, 3, 4.
Okay. Men 1, 3, and 4.
And they choose the same. Women 2 and 4.
Okay. So man 1, 3, and 4. Who could they be paired off with? 2 and 4. So there's no way to match man 1. Why couldn't they do it in order? Why? So there's no way to pair man 1, 3, and 4 off with 3 different women because they only are adjacent to 2 women. And notice M2, man 2, is willing to be paired off with anybody. okay? Yes, it's dated, and they talk about marrying, and so I can't marry all 4 men off, and I certainly can't marry all the women off, even if everything was nice, even if this problem didn't exist, I couldn't marry all the women off because
Or not met.
they're not enough men. Okay, so immediately I'm not gonna be able to pair all the women off, but I wanna maximize the number of men that I can pair off. Now let's throw men and women out. I have what kind of graph is this? This is a bipartite graph. This is a bipartite graph. What is, remind me, bipartite? It's been a long time since we used these terms. Bipartite means I can partition the vertex set into 2 sets of independent vertices. So I can partition the vertices into 2 independent sets. And now, are there conditions where I can match, let's say the bottom set is smaller, is there a condition where I can match everybody in the bottom with a different person in the top? Okay, so that's what we're going to be looking at. Okay, so there's these 2 problems on page 262, where it's essentially the 2 problems we just spoke about. The assignment problem. So I have M applicants for N jobs. And each applicant is applying for some number of these jobs. Under what circumstances, when can I pair each applicant to a job that he or she is able to do? Maybe the job restriction on problem number 7.2.1, maybe the job restriction really corresponds to the fact that C is unable to do job 2 or 3. Okay, so I mean we've got conditions based on what the vertices represent. The marriage problem is I've got M men and N women, and there's some acquaintanceship between the men and women, and is it possible to marry off all M men with the N women? Of course, unless M and N are equal, then there's no way we're going to be able to pair them all off with each other. So, of course, we're only going to be able to look at the smaller of the 2 sets. In this case, the set of men is smaller than the set of women, back on 723. The set of men is smaller than the set of women. Even though there's only 4 men and 5 women, I can't pair them all off. Okay? So, what I want you to do is so I've got these two problems, and now what I want you to do is look at questions 712, 722, and 723. And then we'll...
Are the assignment and marriage problems the exact same thing?
Parts 1 through.
Are they the same thing?
Yes.
So take a look again, the assignment problem and the marriage problem. Are they in fact the same thing? Seems like. So how would you
Represent each problem
relate one to the other?
with a bipartite graph.
They're all bipartite graphs, right? Right, men and women. There's no edges between the men. There's no edges between the women. So we have a bipartite graph. Obviously, there's no edges between the applicants. There's no edges between the jobs. A job can't do another job. So we have 2 independent sets. So
Oh,
as
nice.
far as being a bipartite graph,
Okay, so
they're
is
similar.
AU a match?
Is a matching of the men and women
AU is not
the
a
same
match.
as
By definition,
an assignment of
independent
people to jobs?
edges.
Seems like it.
Yeah, okay.
Yeah.
That's what you have to convince yourself.
Would be a match.
Can one edge be an So
What is a match?
by definition, it's a set of independent edges.
I was thinking vertices, but now I'm,
Unless he went on, hang on a second, maybe there's, no,
So
that
it's a
says,
set with only one edge.
I think it would be. I can Google this. Can imagine made like one edge.
Oh, matching.
so yes, it's, so we can say yes because no two.
This second doesn't exist. For any two you choose, your statements are false. That is true.
This one is AB, what is it? AB and CB?
A, B, and C, D.
CB.
So there's two B's. So we have to say that's not a match.
AB. That's CB. Because they're adjacent.
Jason.
Yeah, so you share.
Sure, it takes me one.
Really, you need a picture to do some of this.
A, U, B, B, and C, W.
That sounds fun.
Yeah, I think it is a matching. A, U, B, B, and C, W.
I'm sick just because it doesn't repeat any letter. No, yeah, no.
So like the first two, A and the U, there's no repeat of any of those.
There's no.
What was the last one, CW?
So yes, TV channels.
Two matchings are different if they are different as sets.
Do they mean just like the vertices?
I don't know, I'm not sure I understand the question. Two matchings are different
Oh, okay.
if they're different as sets.
So like if you compare, like you write one as a set, you write the other one as a set, and if you union, or no, if you intersect them.
There's no
it's-
intersection.
Yeah, it's the internet.
And then find three different matchings.
Wait, is it or maybe not? Maybe it just means they're not the same set. Never mind. I'm gonna
Three
say,
different matchings, that's crazy.
because a set can be different from another set, but still share elements.
And I'm thinking they want us to come up with three, like, I, that are not the same.
Like, they can't be telling us to find three sets of three matchings.
Yeah, I think we can repeat edges, but we can't repeat all three edges.
Technically, you could say AU is a matching, BV is a matching, and CX is a matching.
Yes, but they want each matching to have three edges in it.
So it has to look like I.
So you use I, right, that's one. And then I'm gonna use the first two again and CX, because no one used X yet. And then that means that it leaves space open for you to use A, B, B, W, CX. So bam.
What'd you do?
I did these three,
Mm-hmm.
and then I did these two and this one, and then I did that. So none of them use the same three edges, but I repeated AU each time.
And can you find a G? Can you find a G? Matching up four edges.
G is
This is G. This is G. It says up here. It has partitions X and Y.
Oh, can you find NG and matching?
Yeah.
I'm sorry. I'm saying no, because.
We would have to have- Yeah, so it would have to be a fourth in X. So would we just say no because there's not enough, there's regardless of what's in Y.
All edges are incident to the partition X, which is only besides the result.
Let G be a graph of order n greater than or equal to 2, let M be matching G at most.
Well, are we assuming that this graph is connected? Disconnected.
I would say yes, because M is a non-empty set, so there has to be at least one edge in this graph. Well, you don't know if it's connected, right? But I was just
Can there, if the order is, if it has more than 2 vertices,
you know, for the base case.
can there, well, if it's disconnected, there could be infinite.
That's why I'm guessing it.
It's gotta be connected.
Well, if it was disconnected,
It could
it'd
go
just be the same set over and over, so that's only one set.
So how do you make it out?
No, if it was disconnected, can we just
Like
do
if it was
this?
just one edge.
Like on and on and on.
Oh, like that.
Yeah, there would just be infinitely many
But
varieties
there's-
P2s if it was a disconnected.
If you had infinite
Connected graph.
graph.
So you have
Otherwise,
those
it's
two.
nothing.
It's gotta be a connected graph.
Nice.
I mean, unless it's an infinite graph, there is a limit to the number of combinations you can make of these edges.
Disconnected. P2.
Right, it does make sense, but for this problem, I would have to assume we would talk about.
Do we assume where it says let G be a graph of order n greater than or equal to 2 and let M be a matching G? Do we assume that G is connected?
Right.
You don't have to.
I was just about to say that.
There's no limit then.
I think they're saying what's the largest the M could be. So like, it wouldn't work for every graph. But for some graphs,
If it was
if we're
this,
trying to maximize M,
So
we can
most
make
how
the
many
graph.
edges can M?
well, if it was a disconnected graph, couldn't you just keep writing incessant P2s? And then,
You could. I mean, I think this, you know, all this wants to know is if I have a matching with M vertices, how many, with M edges, how many vertices must it have? Okay, so if I have a matching that has a matching, then it must have two times this number. That's the number of vertices. That's all it's
So when let G contain M vertices, then it has 2 M.
yeah,
so in other words,
I mean,
when
M edges that has 2 M vertices.
I get.
so when you get to part B, okay, so now if I'm gonna have a five edges in my matching, I gotta have 10 vertices, at least. Can you find a tree that has
Exactly.
a matching that has exactly
10 vertices.
vertices?
And
A
5
tree.
edges.
Right, he said a tree.
Find a tree that contains.
A tree of order
the
10.
matching. Sure.
Now, a tree is connected though, so how do we, it's okay, they just won't be matching, not everybody will be matching.
Yeah.
That's what you did too.
I wrote that, well, I wrote P10, just a one.
Because every other,
Yeah.
okay, yeah, yeah,
So there's 9, yeah.
yeah, and it's not a cycle, so you're okay.
Okay, how you making out? Can you find, let's go through these. Some of them are pretty straightforward. Is there a complete matching from X to Y in the top one? One more time, does G have a complete matching from X to Y? Have we been doing the same problems?
Yeah, I don't think we used the word complete matching though, so I wonder if that's what it was.
Oh, I see, okay, sorry. Sorry, let's, so complete matching is one that, so if I have a set X, and then a complete matching would contain all the vertices in X. There's a set X of vertices. And he's really at this point primarily thinking about bipartite graphs. But in fact, everything that we're going to do for bipartite graphs has an equivalent observation or equivalent problem for not bipartite, for non-bipartite graphs. So if I have a set of vertices, complete matching would contain all the vertices of X. Okay, it wouldn't contain all the vertices of the graph. Well, let me see. If I look at A on the top of page 265, could I have a matching that contains all the vertices in that graph? Why not? One more time. On part A, G, the graph is labeled G, could I have a matching that contains all the vertices in this graph? Why not?
One partite is bigger than the other.
Okay, so one of the things that's going to be required if I want a matching of all the vertices, if I want a complete matching for all of V, then certainly I must have that the order of X must equal the order of Y. If I'm looking at now just a bipartite graph, then I certainly must have the same number of vertices if I'm going to have a complete matching. Is that enough? So again, I can, let's imagine that this is a bipartite graph. So this is independent, and this is independent, and there are n vertices here and n vertices here. Do I necessarily know that there's a complete matching, a matching with n edges in it? Or can you give me a graph that doesn't? Let me make it even easier. Can you give me a tree on 6 vertices that has every tree is bipartite. Every tree is bipartite. Can you give me a tree on 6 vertices that doesn't have a complete matching?
The star.
What?
The star. The one where.
The star is, that's what's a tree? What's a, oh, let's see, we forgot
No,
what
you
a
have
tree
like
is.
one in the center and then like 5 sticking out.
Oh, okay, wait a second.
I'm not
So,
sure if that's the, yeah,
okay, so this is a tree.
the sea fish.
This is a tree, a star. Okay, this certainly is a tree, but my parts aren't the same size. Okay, so here my bar partition would have 1 and 5. So yes, there's no way that you're going to have a perfect matching, a complete matching in such a graph. So I'm going to ask the question again. Is there a tree with bipartition, where a bipartition has 3 vertices, just a tree on 6 vertices, where the bipartition is 3 and 3, but there's no matching? There's no complete matching, sorry. There's always a matching of some size. So again, I want 3 vertices. I don't want any cycles. I want a tree. So a tree on 6 vertices has how many edges? 5 edges. So I want a tree, 5 edges, and let's see what else. I got n-1 edges, and a tree is also, help me out. Connected. Okay, so I want a connected graph on 5 vertices, bipartition, 3 vertices in each part, that doesn't have a perfect match. Is there such a thing? Okay, so let me help you. How about that tree? First of all, is that a tree?
Yes.
6 vertices. Notice the bipartition. How many vertices are in each part?
3.
3. And in fact, in a tree, the bipartition is unique. Okay, so up to which ones go on top and which ones go on the bottom, the bipartition is pretty fixed. Is there a matching that matches all the vertices in this graph? No. Can someone give me a real quick reason why this graph can't be matched? We can't have a perfect matching. And I'll give you the first couple words. Look at the 3 vertices in the bottom.
They're all adjacent to the same vertex in the other partition.
Okay? So that's not quite enough. Not quite enough. Let me make it a little bit smaller. Let's look at the first 2 vertices on the bottom. How big is that? Is the neighborhood of the first 2 vertices on the bottom? Okay. There's only, notice the first 2 vertices on the bottom are only adjacent to 1 vertex on top. So if I have any hope, let's just make sure, if I have any hope, if I take a bipartite graph, forget trees, if I take a bipartite graph, I don't know what it looks like. I don't want you to think that there's a matching. Okay, there's my bipartite graph. Maybe there's more edges. If there's any hope of having a matching of the top to the bottom, what can you tell me about? I close my eyes and I choose any subset of the vertices on top. How large must the neighborhood if there's any hope of having a matching of the top to the bottom, what can you tell me about the size, the number of vertices adjacent to those vertices that I circled in red?
Should be less than the number of.
Less than?
Yeah.
At least the same.
At less or equal to.
Is it less than? Can it, if I have, well, how many did I circle? 5? I can't see. How many did I circle?
5.
5. If it's less than, if those 5 vertices only are adjacent to 4 vertices, is there any way to match those 5 vertices up?
Oh.
So at least as many.
Oh, okay. So, if I have a bipartite graph, then if this contains a matching, for every subset, let's call this X and this Y, for every subset S in X, the neighborhood of X has got to be greater, the size of the neighborhood of X has got to be greater than or equal to the size of X. One more time. In a bipartite graph, if I have any chance of having a matching, then I close my eyes and I pick any subset of vertices in the top. We could have done the bottom, it doesn't matter, but I pick one of the parts. I take any subset, oh, listen, sorry. Let me make this right. Don't write that down yet. The neighborhood of S has got to be greater than or equal to S. So I take any subset of vertices of X, and I look at the neighborhood, the neighbors in Y. If I have any, if at some point I pick an X and the number of neighbors is fewer than the size of X, if I choose a set X, I chose that X has 5 elements in it, right? If I chose the 5 elements and it was only adjacent to 4 elements in Y, would there be any way to match up X with Y? No. So this is a necessary condition for there to be a matching, and this is just in a bipartite graph. So a necessary condition is that for any subset S in X, the neighborhood of S, the neighbors of S, has got to be greater than or equal to the order of S. So if this is S, and this is the neighborhood of S, for there to be a matching, there's got to be at least as many points here as there are here. Does that, I mean, that's, of course. That should be like, that's an obvious. Now it's the other way, showing that that's an if and only if, that we'll be looking at. Okay, so for Tuesday, I would like you to actually reread or go through up through section 7.2. And then if you look at exercises 1, 2, and 3 on page 266, that's what we'll start with on Tuesday. Again, I will have a review sheet up. I hope I have the review sheet up by tomorrow. We will spend probably a half hour on Tuesday, at least going through what I will expect on the test on Thursday. Have a nice weekend. Okay, I recorded something. I have no idea what I recorded.